Our next topic is the law of definite proportions. And the law of definite proportions says that every compound has a very specific ratio of atoms within that compound. Okay, so for example, carbon dioxide always has one carbon atom for every 2 oxygen atoms. Okay, if you take this concept and you extend it to a mole's worth of that particular compound. Okay, so if we were to look at a mole of carbon dioxide molecules, you know that the molar mass of that compound is 44.01. Okay, if there is a consistent ratio of atoms within that compound, then there's also consistency within the mass too. Because if we know that carbon dioxide weighs 44.01 grams per mole, and we know that there's 1 mole of carbon atoms for every 1 mole of carbon dioxide molecules, well, we know that 1 mole of carbon atoms weighs 12.01. Okay, so if you analyze that and you divide 12.01 by 44.01 and then you multiply by 100 to get a percentage, then you get 27.3% carbon. Okay, which then means that the other 72.7% has to be oxygen. And you should be able to do the math there and see that it supports that. Okay, so again, because the formulas have consistency through the law of definite proportions, there's a consistency in terms of the mass percent of each element that makes up that compound. Okay, and because all molecules of a specific compound are identical, because they have that definite proportion, then that means that those molecules have identical properties as well. Okay, which you know, I mean, CO2 molecules should all have very similar properties in terms of boiling point, freezing point, molar mass, those types of things, right? Their properties should be identical. Okay, well, what happens if you change the ratio? There's another compound involving carbon and oxygen that you've heard of called carbon monoxide, which is 1 carbon atom for every 1 oxygen atom. Okay, that's a very different percentage. It's a 1-to-1 ratio because the formula is only CO. So that means if you were to analyze the percent composition of carbon monoxide by mass, you'd find out that that compound is 42.9% carbon and compared to the 27.3% in CO2 and 57.1% oxygen. Okay, this difference in these percentages is responsible for the difference in properties. Okay, because they have different proportions of the atoms within the molecule, those different proportions comes from different types of bonding, different things going on, and as a result, the properties of those 2 compounds are very different. So even though those 2 compounds are both made of carbon and oxygen, they have very different properties because their ratios are different. Okay? The fact that we can have more than 1 compound between carbon and oxygen represents something called the law of multiple proportions, which says that, different atoms can combine in different ratios to form different compounds. Another example that I would give you is like H2O versus H2O2, which is hydrogen peroxide. Those are 2 compounds that occur between hydrogen and oxygen, but in different percentages with different ratios. Okay. Organic chemistry, which, at some point in college, most of you will probably take. Organic chemistry is the chemistry of carbon, which is really about like how a lot of times hydrogen and oxygen all bond with carbon. There are thousands of molecules that have carbon and hydrogen and oxygen in them in different ratios. Okay, so that's an example of how multiple proportions are very, very common. All right, I just want to do a couple quick examples to show you mathematically how this concept would come in handy. Okay, so the first one is, what is the percent by mass of each element in methane, CH4? Okay, well, the first thing you want to do is you want to find the molar mass of CH4. So 12.01 for carbon, and then each hydrogen is 1.008, but there are 4 hydrogens, so you need to multiply that. And when you do, you get 16.042 grams per mole. Again, I'd encourage you all to use the periodic table you were provided. Okay, so to figure out the percent that's carbon, we're going to do 12.01 grams divided by 16.042, okay? And if you do that, you can probably hear my calculator clicking in the background, and you multiply by 100. Sig dig wise, just to keep you mindful of that, I have 4 sig digs with carbon, so I'm going to keep it. I'm going to say 74.87% carbon. Okay, now realistically, I know hydrogen should just be that subtracted from 100. Okay, so 100% is CH4 minus 74.87 should give me 25.3%, which I'm going to go ahead for you and verify. Okay, so it's always good just to double check. So 4 times 1.008 is 4.032 divided by 16.042. And just for math, you can see that we're going to be right, because you know that 4 is 25% of 16, so obviously we're right on track there. But just to do the little extra math here, you get 25.13%. And I should have written percent carbon and percent hydrogen. So that's how you can analyze the mass percent or the percent composition of a particular compound. Okay, let's talk about how this comes in handy, all right? Sometimes chemists might use this concept of percent composition to help identify a compound, okay? So in example 2, it says 18.5 grams of element X reacts with oxygen to form 22.3 grams of an oxide, which we know has the formula X2O. Determine the atomic mass of element X, and then what is its identity? Well, let's think about that. So we know that this entire compound right here, X2O, like the sample that they have weighs 22.3 grams, okay? We don't know what X stands for, but we do know that the other element involved in this compound is oxygen. And we know that 18.5 grams of that 22.3 comes from element X, okay? So that means if you subtract 22.3 minus 18.5, that means that 3.8 grams of that particular compound comes from oxygen, okay? And that's useful because we know that we can figure out the mass percentage of oxygen in this particular sample, okay? So 3.8 divided by 22.3, okay, equals about 17% oxygen, okay? So that's useful to us because then that tells us what we can understand about like 1 mole of the compound, for example, okay? Because we know that 1 mole of this compound, since there's only 1 oxygen atom, is going to have 16 grams of oxygen, right? Because we know oxygen weighs 16. all right, and there's only 1 mole of oxygen for every 1 mole of X2O. So 16 grams is going to be from oxygen, which means that 17% of the molar mass of that compound is going to be equal to 16 grams. So if you divide this like this, okay, then you get 16 divided by 0.17, okay, and that gives you about 94 grams, we'll say, which equals the molar mass. Okay, well, again, what does this tell us? Well, this is the molar mass of X2O. We know 16 of those grams come from oxygen. So 94 minus 16, right? So 94 minus 16 leaves you with 78. And we know that 78 grams represents those 2 moles of X. So we need to find out who X is. So we're going to have to divide by 2, okay? And when we do that, we get 39. So the question is, looking on the periodic table, okay? And to give you a little bit of a hint here, all right? You also need to think about bonding principles. We have X2O. You know that oxygen has a 2- charge, okay? So logically, which column are we looking in here for element X? Realistically, we're expecting X to have a charge of +1, which means because we would need 2 of them to balance out the oxygen, which means we're looking at the alkali metals, okay? So look at the alkali metals. Who has a mass of 39 grams, right? Correct. Potassium. Okay, so element X equals potassium because potassium has a mass of approximately 39 grams.